All right, hello chemistry class. Good to see you again. We are going to look at the review questions for chapter 14. And you're not going to have to answer all of these because we didn't cover some of the material in chapter 14. So I'll make sure that you know which ones you have to answer along with me and which ones we're just going to skip for now. Okay? So number one says, although HClAq, that means this compound is dissolved in water, exhibits properties of an Arrhenius acid, pure HCl gas and HCl dissolved in a nonpolar solvent exhibit none of the properties of what's called an Arrhenius gas. Explain why. Well, let's go back to what we defined as an acid according to Arrhenius. It was if the compound, when put into water, breaks apart into ions and specifically breaks apart and forms the hydronium ion, because this H plus and Cl negative are the two ions that are coming from the HCl. And this H plus combines with a water molecule in the water solution to make actually H3O plus. That is called your hydronium. So if the compound, when you put in water, is increasing the concentration of hydronium ions, then according to Arrhenius, it is an acid. Well, if you just have HCl gas, it's not in water. It's not going to break apart into ions. Or if you take HCl and dissolve it in non-polar, water's polar. If you put in something that's non-polar, it's not going to break apart into ions. So the gas HCl and the HCl in a non-polar solvent are not going to break apart into ions and increase the concentration of hydronium ions. It only happens if you take HCl and put it into a polar solvent like water. Okay? Number two, what distinguishes strong acids from weak acids? It's very simple. A strong acid is going to completely ionize. It completely, all HCl is a strong acid. When you put that into water, every HCl molecule is going to break apart into ions. It completely ionizes. You will not have any HCl left in that solution. It's all going to be hydronium ions and chloride ions. Okay? Assuming that it all dissolves, okay? But it is going to completely dissociate. A weak acid partially ionizes. Now, what do I mean by that? Here's an example. A weak acid would be like HF. What that means is when you put that into water, yes, some of these HF molecules are going to break apart into H plus, that is going to combine with the water and give you hydronium, and the F negative. But then some of these hydronium and fluoride ions are going to turn back into HF. And it's only going to be a partial ionization. It's not going to be complete, meaning you're going to have hydronium ions, fluoride ions, and also some of the HF molecules in the aqueous solution. You're still going to have some of this. Not all of this molecule is going to ionize. Not every one of those molecules is going to ionize. It only partially does. That's what's considered to be a weak. And you'll know it's weak because there's a double arrow. A strong acid, when we show the ionization, the reaction is always going to have just one arrow in the forward direction. Okay? Number three, what determines the strength of an Arrhenius base? It's very similar. The strength is determined because of how well it ionizes. So here is a strong base, NaOH. Okay? When you put that into water, every NaOH unit is going to break apart into sodium ion and hydroxide ion. Complete ionization. If that happens, it is considered a strong base. A weak base is only going to partially ionize. By the way, remember, there's kind of two ways where the hydroxide ion concentration can increase. It can be a part of the formula for the base, And so it's going to be created as an ion when you put it into water, or it can come from the water. So when I put NH3 ammonia into water, the NH3 is going to steal an H from the water, and it is the water that's going to become the hydroxide. And the NH3 is now going to become NH4 plus. It stole an H plus from the water, and now the water is going to be the hydroxide. The hydroxide ion concentration still goes up because you have water molecules turning into hydroxide. But this only partially happens, and so this is considered a weak base. Okay? You don't have to answer number 4. We really just focused on the Arrhenius definition for a base, so you don't have to worry about the other definitions at this time. Number 5, what is the trend in the favored direction of proton transfer reactions? So what that means is, remember I told you that, here we'll just stay with this. When you have HCl and you put it into water, it is the acid that is going to donate an H+. So HCl is donating the H+ to the H2O to make that H3O+. Okay? And then what does the HCl turn into if it gives up its H+? It turns into the chloride ion. So the favored direction for proton transfer reactions is, the favored direction is always the one that has the stronger acid on its side. So on the left side, it is the HCl that is going to be acting as the acid, donating its proton, H+, to the water. If we look at the reverse direction, it would be this. If the reverse direction happened, it would be this hydronium ion that would have to transfer the H+ back to the Cl to go back to what we originally had. But HCl is so strong compared to this hydronium. It's much weaker than the HCl as far as an acid, okay, that the direction that's going to be favored is always the direction from the strong acid side to the weak acid side. The strong acid is going to push. It wants to dominate its reaction. Its reaction is to go forward and donate this H+ to the water, and so it's going to push more, a little strongly to its forward direction. This is the stronger acid. Okay? Remember, the acid is always going to be paired with, it's going to turn into the base on the other side, and the base is going to always turn into the acid on the other side. Now, if I was to compare the bases, all you do is, you know that the strong acid is going to turn into the weaker base, right? And the weak acid is coming from the stronger base, if you were to compare the bases. All right? Okay, number 6, it says, use the table to relative strengths of acids and bases from section 3 to determine which of these acids is the strongest and which is the strongest base. Okay, now all you have to do is, I'm not going to go through this because you can easily look at the chart, but I'm just going to tell you it's just as simple as looking at the chart. We'll scroll up there really quickly, and all you have to do is compare. All right? All you have to do is find the formulas that are being talked about in that problem and compare. On the left side are the acids, and the increasing acid strength goes up. So these are the strongest ones up here. Strongest up here, acids. Okay? But then over here, the conjugate base that it would create when it gives up its proton over here, these are the weakest bases because the strength actually increases going down over here. So all you have to do is find your formula from the problem and compare according to this chart. Okay? And I'm sure you can do that. That chart you can use on the test or quiz and refer to it. Okay? Number 7, explain why the conjugate base of a strong acid is a weak base and the conjugate acid of a weak base is a weak acid. That sounds very confusing, right? But I kind of explained it earlier, and I'll go through it again here. Let's go through and let's use a different example here. Let's go to this example here with the ammonia. This ammonia is going to accept, this time it's going to accept the H plus from the water. So the water is acting as an acid, and the NH3 is acting as a base. And over here, the NH3 is going to accept the H plus and turn into NH4 plus. The water is going to give up its H plus and turn into OH negative, the hydroxide. Okay? So the acid on the one side is always going to turn into what is going to be the base on the other side. And the base on the one side is always going to turn into the acid for the reverse direction. Okay? Now, let's compare these. This is going to be actually a reversible reaction because ammonia is a weak base. Let's use our chart to compare. So what we're going to do is we're going to look at H2O. Notice H2O is acting as an acid here, right? Up here, H2O is acting as a base. It's amphoteric. Remember that. It can act as both. We're gonna compare water and ammonium on our table. Let's go back up here and compare. So water, here's water. All right. And we have ammonium. Ammonium right here is above water on this table. So it is stronger as an acid than water is. So let's go back down here. If it's stronger, what it means is it wants to dominate the direction that it favors. Okay? It's going to push its reaction a little bit more hard than the other acid. So this is the stronger acid in this reaction. This is the weaker one, the water. Which means this ammonium is going to push its reaction, the reverse reaction, a little more strongly than the water is. I'm going to make a bigger arrow in the reverse direction, and the forward direction is a little bit smaller. Okay? So what does that mean? If this acid, the NH4 plus, is stronger, what that means is it wants to really donate its H plus. It really wants to donate the proton. It pushes that proton on the OH negative, the hydroxide, and really shoves it and is more strong in its reaction. So it's going to push the reaction the other direction a little more strongly, and it is going to be the water that kind of loses out in this tug of war, or this push of war, if you will. It's pushing both directions. Okay? So the stronger acid means over here it's paired with this base. This must be then the weaker base because it is not accepting the H plus, the proton, as readily from the water as this hydroxide is. This hydroxide is really going to accept, this is the stronger base, really going to accept the proton from the NH4 plus because it's the reverse direction that is getting emphasized. Okay, so the strong acid here is always going to be paired with, over on the other side, the weaker base. And the weak base sorry here. So weak base is a weak acid. The conjugate acid of a weak base is a weak acid. Okay, so in this case, I'm looking at this is actually a weak base here. This is a weak base, and it is paired with a stronger acid. Okay, so that's what the first thing is saying. A stronger acid is always paired with a weaker base. Okay. If I had let's see here, a weak acid, Let's take a weak acid for an example here. Let's look at a weak acid and a weak base. A weak acid would be like HF, okay? And when you put that into water, it's going to make the hydronium and the fluoride. Well, this HF is weak because it's weak. It's going to be paired with a weak base. It turns into this right here. This HF is going to donate its H plus to what? The water. It donates its H plus to the water. And if I compare HF and hydronium, let's compare those two and let's see what happens here. HF and hydronium. Here's our table. HF and the hydronium. Notice the hydronium is stronger acid than HF. So if I go back down here, this hydronium is going to really want to push its reaction. Well, what is its reaction? Its reaction is the reverse direction. It's this way. It's that way. It wants to push that direction. So this hydronium wants to donate H plus to the fluoride more than the HF wants to donate it to the water on the other side. So this is my stronger acid, and it is going to be paired with the weaker, the water, which is acting as a base, but it's going to be a weaker base. Okay? This fluoride is really going to accept the H plus from the hydronium, and both are going to push the reaction back the other way. Okay? All right, name each of the following acids. Now, you don't have to name the ones that have oxygen in them. You can just look at the chart. This is this is nitric, nitrous, I think this is chlorous acid, this is sulfurous acid, but the ones that I want you to be able to name are the ones that are binary, just two elements, hydrogen and then a nonmetal, reactive nonmetal. So this is hydro, because of the hydrogen, hydrochloric, chloric acid, okay? Hydrochloric acid. And this is hydro sulfic, or sulfuric maybe, maybe it's sulfic, sulfuric, hydrosulfuric maybe, hydrosulfuric acid, okay? Hydrosulfuric acid. The hydro because of the hydrogen, and then you've got the nonmetal root, and it ends always in IC, okay? Hydrosulfuric acid. So hydrofluoric would be HF, hydroiodic would be HI, and you don't have to worry about C and D, okay? You don't have to worry about number 10, you don't have to worry about number 11 for now. Let's look at number 12. It says complete the following neutralization reactions. Neutralization is happening when you have an acid and you add it to a base. Okay? Balance each equation and then write the overall ionic and net ionic equations. So let's see what's happening here. What's going to happen in this reaction is both acid and bases are going to ionize. And it is going to be the H plus that is going to combine with the OH, and then the cation, in this case the metal, is going to combine with the anion nonmetal in the other one. They're basically going to switch partners. It's like a double displacement reaction, and we've talked about those before. So I'm going to take the K and the NO3 and combine those together. And K is a +1 ion, NO3 is a -1, so I just need one of each of those. H plus is a +1 ion. OH is a -1 ion, so I just need each one of those. And I'm going to write it like this: HOH. It's just water. HOH is just water. Okay. So this is aqueous, meaning it's dissolved in water. This is aqueous, it's dissolved or ionized, dissociated in water. And then this, if I look at the formula here, this is going to dissolve in water. This is soluble. It's going to dissociate into its ions as well, AQ. And this is just water. It's just a liquid, pure water. So you'll notice then what happens is you have nitrate ions here. You've got potassium ions here. You're also going to have nitrate ions here and potassium ions here because those are all AQ. So those are just going to cancel out. Remember, those are spectator ions. So really the only reaction that is really happening here is the H plus and the hydroxide ion from separate formulas, the H from the first one, the AOH from the second one, are really turning into H2O, water. That is what's happening when a neutralization reaction. And yes, you're going to have this salt, potassium nitrate, in the water as well, but it's not forming a compound. It's not a solid. They're staying as ions. It is going to give it the water salty taste, of course, but it's not forming a new compound. They're just going to be ions in the solution. Likewise here, you have calcium and the nitrate are going to come together. And then again, the H plus is going to join with the OH. So let's write this one. Calcium is going to combine with the nitrate. Now the formula here, calcium is a +2 ion. So I'm going to need 2 nitrates because nitrate's only a -1. And then the water and the OH are going to come together again to form HOH, which is just water. I should say the H plus and the OH are going to come together to form water. That's the H plus and the OH. And now let's balance it. I have 2 nitrates on the right side, so I have to double this. And when I do, I think now I have to double that. And then I should have a balanced equation. Again, if I just cross out those ions that are not doing anything, they're just ions on the left and the right, they would be the calcium, it's in an aqueous solution, and the nitrate, it's in an aqueous solution. And over here, if we check our solubility table, calcium nitrate is also soluble. It's going to dissolve and dissociate into ions. So these are all ions. So the calcium is an ion on both sides. It is in aqueous solutions. The nitrates are in aqueous solutions on both sides, but it is the H and the OH that form pure liquid water. So the OH, you got actually 2 of those, okay? But this is really going to be kind of redundant. I can cancel out the 2's once I write this net ionic equation. 2 H pluses are forming 2 waters, okay? Or if I just reduce all of that, it's simply, again, just the hydroxide and the H plus forming water, okay? All right, 13 we're not going to do. 14 is a great problem. It says write the formula equation, the overall ionic equation and the net ionic equation for a neutralization reaction that would form this salt. Remember, a salt in chemistry is just an ionic compound. So we're forming RbClO4. Here's the metal. Here's the polyatomic nonmetal. That's the salt that's forming. Look up here. Do you see this? Here was our salt that was being formed. Here was our salt that was being formed. So we can see that the calcium, the metal, is coming from one of the formulas. Looks like it's coming from the base. The polyatomic nonmetal here, the nonmetal is coming from, that's the anion, that's coming from the acid. So all I have to do is just add my OH to the metal part of the salt and my H to the polyatomic nonmetal part of the salt. My salt is RbClO4. And I know the other product is going to be water for the neutralization. So where's that coming from? The Rb is the metal part of my base, and the Cl4 is the nonmetal part of my acid. And that's it. That's how easy it is. This Rb goes with OH, the metal goes with the OH, the nonmetal, the polyatomic nonmetal goes with H, and there you've got your base and your acid. And again, aqueous, aqueous, this dissolves, it's soluble, this is aqueous as well. This is pure liquid water, and you'll notice that the rubidium is aqueous on both sides, the chlorate is aqueous on both sides, so again it is just the OH negative combining with the H positive to form your liquid water. Okay? Alrighty. Now we're going to actually be doing some stoichiometry as well, because we got to remember that. We can't forget our stoichiometry. Okay? It says 211 grams of barium carbonate reacts with a solution of nitric acid to give barium nitrate, carbon dioxide, and water. If the acid is present in excess, what mass and volume of carbon dioxide gas at STP will form? What a great problem. This reviews a lot of stuff, so it's good to go over things that have multiple concepts in them. Okay? Let's first of all look at our reaction. Barium carbonate reacts with nitric acid. And you can look up the formula for nitric acid. Okay. To give barium nitrate, what's going to be the result here? Barium nitrate, barium NO3. Now, barium is a +2, nitrate is only a -1, so this would have to have 2 of those. Okay. And carbon dioxide and water. Okay, and water. Now let's make sure this is balanced. I've got 2 nitrates on this side. I'm going to have to double this to have 2 nitrates. Now I have 2 oxygens in the water. I've got 3 oxygens. Yep, that's good. And a carbon. Okay, we're balanced. Very good. It is balanced. So hopefully you remember how to balance the chemical equation. What we want to do now is we are starting with 211 grams of barium carbonate. This is our mass here that is given to us. Remember the table that we set up? Mass, molar mass, moles. Okay? And what do we want to find? If the acid is, this is in excess, we don't have to worry about this one. What mass of carbon dioxide? We want to find this. Okay? We want to find the mass of carbon dioxide. Okay? So we got to go from mass of barium carbonate to moles of barium carbonate, then from barium carbonate moles all the way over here to moles of carbon dioxide, and carbon dioxide moles down to its mass. And we do those steps from mass to moles using the molar mass. So let's look up the barium carbonate molar mass. Let me look that up. Okay, the barium molar mass is 137. I'll do this on the side here. About 137. Then you've got a carbon, which is 12. And you get 3 oxygens. 3 times 16. So 3 times 16, that's 48, right? So you have to add all that up. 48 and 12 is going to give me 60 plus the 137. I think that's 197 if I did my math right there. Okay? 197 grams per mole. Well, I don't have a 197. I got 211. It's pretty close. It's pretty close. But it's not exact. If I did my math right here, 211 divided by 197, it's about 1. Okay? So if it's okay with you, I'm just going to use 1. I'm just going to round to 1 to make the math easy for you. So we have 1 mole, about 1 mole. Not exactly. A mole would be 197 grams. We have 211. It's pretty close. So it's going to be 0.9 something. This 1 mole produces the same number of moles of carbon dioxide. Look at the balanced equation. One of these produces one of these. So this also is going to be 1 mole. Okay? That also is going to be 1 mole. Now I have to take that 1 mole and find out what its mass is. I need the molar mass of carbon dioxide. 1 carbon is 12, 2 oxygens, 16 each is 32. That's 44. So I have to take my 1 mole and multiply by 44. So that's 44 grams. Okay? Now I have the mass of my carbon dioxide. How would I have to find the volume of that? It told me it's at STP. And if you remember, think back to our chapter on gases. At STP, the molar volume of any gas is 24 liters. So since I have 1 mole, that's nice. A mole and it's at STP, then my volume here is going to be 24 liters. Okay, 24 liters. If I only had like, now if I did this right, I know I kind of rounded that up. Let's say it was 0.9 moles, all right, 0.9, and this was 0.9, then I'd have to take 24 times 0.9 to find the actual volume. Okay? All right, great. That was a good problem. Number 16. Now I'm going to leave this one a little bit more to you, but I'm going to show you how you can set it up. Okay? So on this one, we've got two reactions. What they're saying is you're going to start with this amount of SO2. Okay? And it's a two-step process. This SO2 is converted into SO3, and then the SO3 reacts with water and is turned into the H2SO4. So we want to go from SO2 to SO3, and then SO3 to H2SO4. Okay? So I'm going to write it this way. I'm going to write down both reactions. And I'm going to show you the steps, and then I'm going to leave the steps up to you. This is the mass that we are starting with. Okay? We're starting with 3.5 times 10 to the 8 kilograms of the SO2. This is your mass. Okay? You might want to change that to grams because the molar mass is in grams, or you can change the molar mass from grams to kilograms if you want. Okay? But you're going to have to do this. I'll show you the steps. You're going to have to take this mass and convert it into moles by dividing by the molar mass, okay, of SO2. You look on your periodic table, look for the molar mass of S, add it to 2 times the molar mass of oxygen. That's going to go here, and you're going to divide by that number. You're going to divide by the molar mass. 3.5 times 10 to the 8. Actually, let's go ahead and change that to grams right now. I would multiply by 1,000, right? There's 1,000 grams in a kilogram. So 3.5 times 10 to the 8 times 1,000 is going to be 10. I'm just going to add 3 to the 8 here, right? It's going to be 10 to the 11. So that's how many grams. You take this and you divide by the molar mass that you're going to get from the periodic table. That's going to give you the number of moles. Then you'll notice it is a 1-to-1 ratio here. This number of moles right here is going to be the same for this number of moles. Okay? That's for the first reaction. Then you steal that number of moles for the second reaction. It's the same formula. See that? SO3. And you take this, and now it is a 1-to-1 ratio here as well, a 1-to-1, and you're going to have the same number of moles there. Then you convert that into mass by multiplying by its molar mass of H2SO4. 2 hydrogens, 1 sulfur, 4 oxygens, multiplied by its molar mass. Then you have your answer down here. Okay? And you're good. Not too bad. Oh, that answer will be in grams. This will be in grams. So then we would divide by 1,000 to get the answer in kilograms. Okay? And there you go. All right. I hope that helped you tremendously. We're talking about acids and bases, and we threw in a little stoichiometry there for you as well, just to make sure you're keeping that current and fresh in your mind. Okay? Let me know if you got questions. Let's keep working hard, and little by little, we're going to get it.